6. 1 plus 2 plus 3. The divisors of 6, not counting itself, add back up to 6. 28. 1, 2, 4, 7, 14. Add them. 28. A number that does this is called perfect, and perfect numbers are old. The Greeks had 4 of them before anyone had algebra. Here is the question that has haunted mathematics ever since. Every perfect number anyone has ever found is even. Is there an odd one? Nobody knows. Nobody has known for 2,300 years. And that is not for lack of trying. Let me show you the even side first, because it is completely solved. The first 4 perfect numbers are 6, 28, 496, and 8,128. Look at the pattern. 6 is 2 times 3, 28 is 4 times 7, 496 is 16 times 31, 8,128 is 64 times 127. Each one is a power of 2 times a Mersenne prime. Euclid proved this around 300 BC. If 2 to the p-1 is prime, then 2 to the p-1 times 2 to the p-1 is perfect. 2,000 years later, Euler proved the converse. Every even perfect number has exactly this shape, no exceptions. So finding even perfect numbers is the same problem as finding Mersenne primes, and we have been doing that with computers since the 1950s. Here is the table. P equals 2 gives you the prime 3, perfect number 6. P equals 3 gives you 7, perfect number 28. P equals 5 gives you 31, perfect number 496. P equals 7 gives you 127, perfect number 8128. Jump ahead. P equals 13 gives you a Mersenne prime with 4 digits, and a perfect number with 8. P equals 17, 6 digits, 10. P equals 19, 6 digits, 12. By the time you reach P equals 127, the Mersenne prime has 39 digits. The perfect number has 77. As of October 2024, there are 52 known Mersenne primes. The latest one, found by Luc Durant using GPU computing, has over 41 million digits. The perfect number it generates has over 82 million digits. Every even perfect number in history sits in that table, completely classified. One formula, one search. Now the other side. Is there an odd perfect number? Not one has ever been found. Not one has ever been ruled out. This is not a recent question. Nicomachus, around 100 AD, asserted that all perfect numbers must be even. That was nearly 2,000 years ago. He had no proof. We still do not have one. But here is what makes this problem extraordinary. Mathematicians have not just failed to solve it. They have built an enormous wall of constraints, proving what an odd perfect number must look like if one exists. Every decade, a new condition is added, and the portrait of this hypothetical number becomes more and more absurd. Let me walk you through the wall, and I want you to watch the numbers, because they escalate. 1953. Touchard proves that any odd perfect number must satisfy a specific modular condition. It must be congruent to 1 mod 12 or 9 mod 36. That is a structural constraint. It narrows the search space, but it does not close it. 1974. Haggis and McDaniel prove the exponents in the prime factorization cannot all equal 3. Earlier, Steuerwald had shown they cannot all equal 1. Together with Knold's result that they cannot all equal 2, we know the exponents must be unequal. 2006. Goto and Ono prove the largest prime factor must exceed 100 million. Not 100, not 1,000, 100 million. 2006 again. Pace-Nielsen proves there must be at least 9 distinct prime factors, later improved to 10. If 3 does not divide the number, at least 12. And then the size bound, 2012. Occam and Rao prove that any odd perfect number must exceed 10 to the 1500. Let me put that in context. The number of atoms in the observable universe is roughly 10 to the 80. The number of Planck volumes in the observable universe is about 10 to the 185. 10 to the 1500 is incomprehensibly larger than anything physical. And it does not stop there. Occam and Rao also prove that the total number of prime factors counted with multiplicity must be at least 101, later updated to 115. Here is the full wall as it stands today, size greater than 10 to the 1500. At least 10 distinct prime factors, at least 115 total prime factors. Largest prime exceeds 10 to the 8, not divisible by 105, must be a sum of 2 squares. Exponents cannot all be equal, must satisfy Touchard's congruence, and Euler's structural form, which I will show you next. Euler proved something remarkable about the structure of any odd perfect number. If one exists, it must have the form p to the alpha times m squared, one special prime raised to an odd power. Everything else appears to even powers, squared away neatly. And there are conditions. The special prime p must be congruent to 1 mod 4. The exponent alpha must also be congruent to 1 mod 4. And p cannot divide m squared. This is an incredibly rigid skeleton. It means any odd perfect number has exactly one prime that breaks the pattern of even exponents. Every other prime factor shows up an even number of times. Think about what this means in terms of factorization. A normal number might have any combination of exponents. An odd perfect number must have every exponent even, except for 1, which must be odd and congruent to 1 mod 4. This constraint alone eliminates the vast majority of odd numbers from even being candidates. And yet, combined with every other constraint on the wall, it still does not produce a contradiction. In 1638, René Descartes found something deeply strange. He wrote down a specific number, 3 squared times 7 squared times 11 squared times 13 squared times 22,021. The product is about 198 billion. If you compute the divisor sum of this number, treating all 5 bases as prime, you get exactly twice the number. It looks perfect. There is one problem. 22,021 is not prime. It factors as 19 squared times 61. Descartes knew this. He was not making a mistake. He was constructing the closest possible near miss. A number that satisfies every structural requirement of an odd perfect number, except one factor is composite. This is called a spoof perfect number, or a Descartes number. Let me show you the checklist. Euler's form? It has the form p to the 1 times m squared, with p equal to 22,021 playing the role of the special prime. Check. Congruence to 1 mod 12? Check. Sum of 2 squares? Check. It passes every known structural test, except the one that matters. 22,021 is not prime. It is 19 squared times 61. For nearly 4 centuries, this was the only known spoof. In 2022, Pace-Nielsen's team at BYU found 21 additional spoofs using 3 years of computation, but every single one requires negative exponents. Descartes' original remains the only honest near miss, the ghost that almost passed through the wall. So should we expect an odd perfect number to exist? In 1977, Carl Pomerance built a probabilistic model. Take a large random odd number n. What is the probability that its divisor sum sigma of n equals exactly 2n? The answer is staggeringly small. For a number of size n, the probability is roughly 1 over n. Sum that over all odd numbers, and the expected count converges to something extremely close to 0. By this heuristic, odd perfect numbers should not exist. But here is the twist that makes this interesting. Apply the exact same reasoning to even numbers. What is the probability that a random even number is perfect? The expected count of even perfect numbers by this same model is finite, small, maybe 2 or 3, but there are at least 52. The heuristic is demonstrably wrong about even perfect numbers. The Mersenne prime structure creates a conspiracy, a pattern that defeats the probabilistic argument completely. So when the same heuristic says odd perfect numbers do not exist, you have to ask, is it seeing the truth this time? Or is it missing another conspiracy? Nobody knows. The heuristic is evidence, it is not proof. And in mathematics, that distinction is everything. Let me close with where we actually stand. On the even side, 52 perfect numbers, all of the form 2 to the p-1 times a Mersenne prime, completely classified. The largest has 82 million digits. The formula is 2,300 years old. On the odd side, 0. A wall of constraints so severe that any odd perfect number would be larger than 10 to the 1500, built from at least 115 prime factors, satisfying a structure so rigid that only one prime in the entire factorization is allowed to break the even exponent pattern. One ghost number, built by Descartes in 1638, that passes every structural test but fails because one of its factors is composite. One heuristic that says they cannot exist, but the same heuristic is wrong about the even case. And 2,300 years of silence. The odd perfect number problem is not famous because it is hard. Many problems are hard. It is famous because it is simple. Add up the divisors. Do they equal the number? Every child can understand the question. And the answer for odd numbers is that we have never known. The box is almost closed, but almost in mathematics is nothing.